talk, he will talking about the thermodynamic limits of communication channels.
Thank you. Thanks for the organizers for giving me the opportunity to present my work here. So I'm right now a postdoc at Marseille University. We have a thriving institutional organization, as you can see by the number of affiliations here. But today I will discuss a project that I developed in my previous postdoc in Luxembourg in the group of Massimiliano Esposito. So let's start with the title. The title is Thermodynamic Limits of Communication Channels. Communication channels, if you attended ever in your life information theory course, you can probably imagine like having an alphabet or a binary alphabet where you have zeros and ones and you communicate it across with a channel, and then there will be some noise and you need to decode it. But I will claim throughout this presentation that there are many more systems that can be viewed as communication channels and share their properties. And I will use some results from non-equilibrium thermodynamics to see that actually we can find some thermodynamic limits for the operation of these communication channels. So first, what is information theory? Information theory is one of the most important disciplines nowadays. It is very relevant for computer science, cryptography, machine learning, but also physics. And I would summarize information theory in two main results: that we have a limit for data compression, which is the entropy of whatever message you're trying to get across, and also the rate of reliable communication. So if you want to use one channel reliably with an arbitrarily small probability of error, this rate is called the channel capacity. So these are two very important objects. Of course, the first one, you heard about it many times, but the channel capacity, maybe it's a little bit new. I just want to tell you that it's extremely relevant in information theory. And the second discipline that I will use to get the results of this talk is stochastic thermodynamics, which is, let's say, the field I'm been working on. And as a brief summary, it establishes trade-offs with thermodynamic quantities, especially fluctuating quantities. And it's basically textbook thermodynamics from your graduate course, but out of equilibrium and with fluctuations. So what is a communication channel, the object that we're going to study? The communication channel is defined as an input alphabet, X, the output alphabet, Y, and the transmission probabilities. So the probability that you transmit Y, given that your input is X. The conjunction of these three objects is the communication channel. And this is a famous diagram for the communication channel. So you have a message, and you first encode this message into codes that in this case can be viewed as zeros and ones. And then this code is fed into a channel, and this channel is going to process this code, and there will be some noise, of course, and maybe it's not a perfect channel, and then you decode it to get an estimate of your original message. This is the textbook example of a channel, the binary symmetric channel. You have zeros or ones here, you have one bit, and then with probability 1 minus f, you transmit the correct bit to the output variable. And with probability f, which is the error rate, you transmit the wrong symbol. And so these are the transmission probabilities, and this is the input alphabet, this is the output alphabet, this is a channel. But also, we have many other systems that process information and can be viewed as a channel. So in this case, I take a very simplified model of cell sensing, where you have a receptor that is attached to the membrane of your cell, and some ligand is going to come here and bind to the receptor, and this is going to privilege some chemical reactions, and as a consequence of this binding, the protein Y will get activated more often, and the idea is that the cell, through these concentration of active proteins, uses it as a proxy for the concentration of your ligand, so we can climb food gradients. And the probabilities of having an active protein, given that you have a ligand here, plus your input alphabet that is on and off when it's empty or occupied, and if your protein is active and inactive, is also a communication channel. But also, like CMOS devices, you can be sure that all of your smartphones and computers are filled with billions of CMOS devices. It's one of the most modern technologies nowadays for information processing. We can also view this as a communication channel because you feed some voltage here, and then it's going to go through this circuit where you have two transistors here, and basically it's going to invert the signal on the other side, plus some noise. And this is the input, this is the output, these are the alphabets, and here you're going to have some transmission probabilities. This is also a communication channel. So the big picture is you have a message that is encoded in your input, you feed it in your channel, and then on the readout, you're going to have something like that, and you want to decode. To characterize a communication channel, we use the mutual information. The mutual information is like the relative entropy between the joint probability distribution of x and y and the product of the marginals. If they are independent, the x and y, then this guy is equal to this guy, and mutual information will be 0, which makes a lot of sense because if your input and output are independent, then you don't communicate anything. They do not share information. But we want this to be as large as possible. The channel capacity is defined as the supremum of the mutual information for over all the input distributions. Of course, a channel is going to perform differently depending on your input, in your input alphabet, the distribution of the symbols in your input alphabet. And we take the one that maximizes the mutual information. So the best case scenario for our channel is the channel capacity of the channel. And it is very important because of this theorem proven by Claude Shannon in the late 40s that basically says that you can find a code to transmit information through your channel at a rate R, so number of bits per use of the channel, with arbitrarily small error probability if your rate is smaller than the channel capacity. So yet again, another reason for why the channel capacity is so important. It's the maximal rate of reliable communication. Yes?
R is the same dimension of C? Is R the same dimension of C?
Yeah,
Yes.
R is like measured in bits, and bits per use of the channel.
Okay, thank you.
Now I'll get to the punchline in a second. So let's imagine the scenario where you are feeding your channel with your input symbol x. Then the value of y is going to relax accordingly to what we call the fixed point y of x. And when we measure these, we usually try to infer the presence of x because we saw y of x. Whatever they are, they can be many different things depending on the channel. But as soon as you change your input from x to x prime, then the value of your output variable is going to relax. And maybe this relaxation is not instantaneous, and when you have like a circuit, the electrons have to flow through the circuit, and then it's going to take some time for y to relax to the next fixed point, and this is characterized by the typical relaxation time. So every time you change your input, you're going to have this relaxation. We want to study the average entropy production after switches. If you're not familiar with entropy production, unfortunately, I will defer the definition of entropy production, because tomorrow I'm sure many people will do a better job than me at introducing entropy production, but for now, you can think of it as a measure of irreversibility, or the energy dissipated by the process, the energy that goes to the environment and you cannot recover it back. So this quantity that I introduced here is the average over two input symbols, the x and x prime, both of them are inputs, and the entropy production when you relax from yx to yx prime during this typical relaxation time scale. So you change your input, your system will have to relax. So this is the entropy production in this very relaxation process. The main result, and unfortunately I have to skip the technical details, but it's a very simple calculation, is that the mutual information of your channel is going to be upper bounded by this average entropy production after switches. And this is a very important result, and we believe it's a fundamental result, because it says that the mutual information shared between input and output is limited by the energy you dissipate. And of course, if we find this special probability distribution of inputs that maximizes your mutual information, and we plug it here, on the left-hand side, we're going to have the channel capacity. On the right-hand side, we're going to have this energy dissipation after switches for P star. But yes?
Pedro, what's the difference between both entropy production, this and the prime one?
This sigma star is basically the same one, but calculated with P star. Okay, now let's see how it works. So for the binary symmetric channel, the first example that I gave you, the most simple one, we know, and this is a trivial result from information theory. If you open Thomas and Cover book, you're going to see this result there. The channel capacity is bounded by the logarithm of the cardinality of your input alphabet. So in this case, it's a binary alphabet, so log of 2. This is the maximum channel capacity we can have for the binary symmetric channel. And here I'm varying the error rate. So here my channel has a lot of error, and here has no error. If I plot the channel capacity, I have this curve here. Of course, when I have a lot of error, my channel capacity goes down, and yes, it satisfies the obvious bound. And how does this guy perform here? That's the important question today. And this is the new bound. And it's very interesting that here it is tighter, and here it is trivial in the sense that we knew that it had to be below this curve. So just to finalize, let me share a few thoughts with you. So the first one is that this is the trivial bound, as I just said, the logarithm of the cardinality of your input alphabet. And I would like to give some interpretations to this result. The first one is that better channels cost more. So if you want to have a channel with a very high channel capacity, then you're going to have to pay a thermodynamic price. You're going to have to dissipate more energy after your switches. So you can think of it as the bang for the buck. So if you want more bang, you're going to have to pay more buck. And this is a fundamental thermodynamic limit of channel capacity, and I think it's very interesting because even though there are a lot of works that relate information theory to thermodynamics, I think there is much more to be explored. This is valid even if your channel is in equilibrium or arbitrarily far from equilibrium. So if your channel satisfies detailed balance, you might think, okay, I don't have any entropy production. But since you are constantly changing the input, you keep changing the probability distributions and you dissipate along it. Like the thing is that after you relax, you're not going to dissipate anymore, but during the relaxation you do dissipate. And just to finalize, you can think of it qualitatively in the sense that better channels cost more, but also quantitatively. Let's say that you do measure your channel capacity, but you cannot measure the energy dissipated, so you can infer it. You know how much you dissipate at least, because this is an inequality. So the take-home message is there are many systems that process information and can be viewed as communication channels. And for the communication channels, we know that the energy dissipation is a limit to the channel capacity. This work is done in collaboration with Nahuel Freitas and Masi Esposito, and it's in preparation, and hopefully it's going to be out soon. Thank you.
Thank you, Pedro, for your nice talk. We have time for just a few questions, few questions.
So at an intermediate point, you introduced a switching time, tau. Does the final result depend on tau? Like normally I expect that if you let something go very slowly, you'll have to dissipate less energy, for instance.
Yes, it does depend on the relaxation tau. So you always have this problem that you can define a tau that is larger, and then you're going to account for more dissipation. But we study like the perturbation of the definition of tau, and everything is, let's say the error here is of higher order, and then it is not an issue in the end. But we can find some definitions of tau, like when you are close to the boundary of the next fixed point by an error that you are willing to accept, or you can take the spectral gap of your Markov generator, and it is dependent on tau, indeed, but we have arguments for why the correction is of higher order on 1/tau.
I mean, along similar lines as the previous question. So the result is based on assuming that the channel is some kind of Markov network on discrete states?
Yes.
and then you manipulate rates arbitrarily as a function of the input? How does it, can you say a little bit more on the background
Yeah,
of the
so
proof?
we make a modeling of the dynamics of the channel. So we don't have this abstract notion of just transmission probabilities. So we create a Markov chain, continuous time Markov chain. And there we can define the entropy production, right? And we can calculate the mutual information and also the relaxation between fixed points. And we just need to show that the mutual information is related to the non-adiabatic entropy production. And since the adiabatic entropy production is greater than 0, we get this result. It's very simple. Like I can show you in 2 lines after the talk.
Okay. Last question, please.
Thank you very much. I was wondering, here, related to the other 2 questions, you have a finite time scale. What would happen if that time scale stops existing by some way, like it diverges?
Well, if your relaxation diverges, you're never going to reach your next fixed point. So your channel is already doesn't make a lot of sense since the beginning, right? Because you cannot decode it if you don't relax to the next fixed point. Yeah.
Okay, let's take it again, Pedro.
Thank you.
The next speaker is Adriano Batista from Federal University of Campina Grande.
Thank you.
Okay, thank you. I'd like to thank and praise the organizers for putting together this awesome conference. And I would like to talk about this work. It's all analog, like the previous one. The motivation is from experiments. This is from early 90s on a mechanical resonator that is parametrically excited, pumped. And they observed some interesting properties of fluctuations before the pump is on. The output goes to this lock-in amplifier. These are the two output channels of the lock-in. So it's just the same Gaussian distribution for both output channels. But once the parametric pump is on, then one channel is squeezed and the other one is stretched. But there is a lower limit of 6 dB on the maximum you can squeeze. It's called thermomechanical squeezing, unlike the quantum, but it's a similar behavior in some ways. This is a newer apparatus, another experiment. They tried to go beyond this squeezing limit. They could get below this 6 dB compression with feedback. It's a resonator, and there's parametric pump and feedback. And more recently, some applications of this on membrane, nano mechanical device here with a extremely high quality factor, I think of the order of 1 billion. And they also could squeeze the noise, but they couldn't see cooling on these devices. So the model, it's based on the Vinanti and Falferi work, but I think it's more rigorous mathematically. I put the output of the lock-in here. There's this convolution integral. It's from the lock-in, and here it's all linear. And initially I just used this. It's all coherent drive, no noise here, just to see the amplification behavior of this amplifier. It's below the threshold for instability. That's all. So just a diagram of the lock-in. There's a local oscillator. It's multiplied by the input, and there's a low pass, the RC filter, low pass or RC filter. That's what we get. But then you can transform this from an integral differential equation into this differential equation. And now I can apply the theory I had worked on before on the Floquet theory of this. And I'm interested in, just initially just to get an idea of the boundary between stable and unstable dynamics. And there's some algebra. I convert this to all algebraic equation. And then I can see the gain and the threshold line is when this characteristic equation that's equal to 0. So, and now I can, but this I only get one of the thresholds to instability. We'll see that this other one is connected. The first one is connected to a saddle node bifurcation, and this to a Hopf bifurcation. Also using this harmonic balance method. Then at the end I get these coupled equations, algebraic, and then I can solve them numerically and find this shift. And then this is quasi-periodic behavior. I can get this frequency shift and the pump amplitude for this. So when I'm near this Hopf bifurcation, the transient, in the beginning I can fit this with the averaging method, but then this behavior near the transition, it gets lost, and I can't do the usual averaging technique. But with this analytical method, I can get the peaks. I Fourier transformed only the stationary part here, the quasi-periodic part. So before I do some words on the Floquet theory, the A is a periodic matrix, it's all linear. It's, I can go from this system to the time evolution operator dynamics. And then I use the results of Floquet theorem, that this evolution over a time period of the T, it's given by this matrix. And the eigenvalues are called Floquet multipliers, and the eigenvalues of the exponent are Floquet exponents. And there's another piece of math is that I can go from the dynamics of phi to the determinant of this. And it's related to the trace. In our system here, and I can just solve this easily, and in our system here, the trace is a constant. So I get it's three-dimensional also. When I put the feedback, it increases the dimension of the system. And they have a multiplication of 3 multipliers. It's always less than 1. So now I can have not just a multiplier with modulus 1, but it can also get a pair of complex conjugate equal to 1. That would be a Hopf bifurcation. So here's, I'm varying the pump amplitude from 0 to this value. And then the eigenvalue here, the multiplier, gets into 1 before the pair of complex conjugate. But on the other limits, in the other interval, where Fp becomes negative, the pair of complex conjugate eigenvalues become equal to 1, given the Hopf bifurcation. So I get these 2 boundary instabilities. This is only possible with the feedback. Without the feedback, it would be symmetrical, and I would only have this Hopf, not the Hopf, but only the saddle node bifurcation. So this was not predicted previously. So I also used the Floquet theory with Green's functions to analyze the response to any given input, additive input. This is elastic response of the resonator, and these are up and down conversion, parametric conversions. This X could be any number of any dimension, but in our case it's a 3-dimensional case. And for coherent drive, this is the Fourier transform, and I can get the frequency response and the time response. And from this I can get envelopes, like they will have beats. If it's exactly at the resonance, then we have parametric, degenerate parametric amplification. And we can now check this, both numerical and analytical, and also the Fouquet theory is semi-numerical. And they all agree very well with each other. So this gives me information that if I put noise here, I would get squeezing. One phase would squeeze and the other would be amplified. But if I'm near the Hopf bifurcation, both of them will be de-amplified. So this gives me a hint that I could get cooling in this area, this region, parameter region. So now I use I analyze the Fouquet fluctuations using this Fourier transform approximation and perturbative approximation. Can shift the frequencies and get rid of the Z part. And then once I solve this, I get this algebraic equation. But then I can, with another approximation and frequency shift in here, I can put this equation approximately like this, and it has the same shape form that I had the theory. I had developed the theory before. Only that these green functions are not from the Fouquet theory, but from this perturbative method. And I can compare what I can get. This is just the harmonic oscillator noise spectral density for a reference with what happens. This is when I only have pumping. The peak increases very near the middle, but outside it's basically the same, outside the around resonance. And but when I put feedback, things change a lot. These two other peaks have to do with the complex values of the Fouquet multipliers. And the side bands are split by twice the imaginary part of the Fouquet exponents. This is already slightly, I will see that the first ones, I have heating, effective higher temperature, while the ones near the Hopf bifurcation, I could get cooling. But I cannot get very close to the Hopf bifurcation because it will start heating again. So this, I believe this could be observed experimentally in these nanomechanical systems. And I also investigated squeezing. I investigate, it's different from the other case that here is the noise spectral density of the whole signal, the complex signal, while here it's the real and imaginary parts of the fluctuations, and there's correlation between them. And these results here indicate the squeezing. One of the channels is heated up, and the other it remains very cooled. This is diagonalized after I diagonalize these dispersions. I get this result. So that's what I obtained over here. The final. I think this could be in even classical systems. I mean, big resonators. It could be made even in nanomechanical regime also. And what I would like to do is choose cool down the temperature to reach the quantum limit. And the theory could also be applied to stabilizing the phase states of Kerr parametric oscillators that are used in qubits implementation in superconducting circuits. So that's it. Thank you.
Thank you. Questions? I have. No, make your
No, it's just a quick question. Is your Fouquet theory applicable at all frequency regimes or only at high frequency or low frequencies?
I think it could be any frequency. It only has the parametric
You-
drive has to be periodic.
But you're not relying on any approximation at high frequencies or low frequencies, right?
No, no.
Okay,
not
thank you.
maybe.
You point out some possible experimental applications, but
Yeah.
did you find some results in the literature, or have you
Not for
considered
these
this
hot
possibility?
bifurcations.
But Do you have some result for comparing?
Yeah, this is I did the theoretical model, two theoretical models, the approximate models. The average one I didn't show,
Okay.
but they agree with the harmonic balance, the flow K theory, and numerical integration without noise, and with noise, stochastic
to
differential
agreement.
equations. They all agree. I didn't show the last results, but
Okay.
they all agree.
And more questions? So let's thank him again.
Yeah, okay.
The next speaker is Hector Medel from Tecnológico de Monterrey, Mexico. The title of his talk is Geometry-Driven Non-Equilibrium Phase Transition in Hard Spherical Gas in One-Dimensional Elliptic Curves. Okay, you can start. No.
And now? Okay. Yeah. Well, first of all, I want to thank the organizer for giving me the opportunity to present here. This work was in collaboration with Isaí Garcia, was a former student, undergraduate student, and now he's pursuing his master in a different university. But I want to thank you especially because he was the who want to follow this idea. No? So as the title suggests, what I want to show you is a very a toy model on how the geometry can drive kind of non-equilibrium phase transition in one dimension. This is complicated to understand because we know that it's not possible to have a phase transition in one-dimension systems. But I can show you that there are a kind of two different phases living together. But let me show you. Well, the motivation of this was traffic. When you are in the traffic, when we are in traffic, we can see that if we go to a curved road, we have to slow down, and if it's a straight road, we can speed up. But this is difficult because we can control this. But once I was in introductory course of complexity, and the instructor said something very difficult to me to understand. That was that if you have a kind of Manhattan metric that is a plane grid, this you can map any rail car trajectory to this. And this was very, very hard to me because I know that we go uphill or downhill. Sometimes we have different behaviors. So let me check. Okay, sorry. What I'm doing? Yeah. Oops. So in the simple case that we have an ellipse, we can see that the curvature and the metric is different from different positions. So we thought in a very simple model. What if we had hard spheres on this curve, and they can collide elastically and with no noise, with no other interactions, just collisions. And we put it there. And the point here is that depending on the parameterization, we have different behaviors. So we have to do it in something that is called the
true parametric parameterization in the true angle is the angle of the parameterization that we use when we can follow the movement of planets in the solar system. And we have a fixed point, and we have to relate the real movement of the planet with our reference point. So on this parameterization, we find something very nice, that in the points where the metric is larger, we have the kind of clustering. Something that we later saw that we can find in active matter, in particular in MIPS, that the speed of the particles slow down depending on the density, if the density is higher. So we just put all these things together and then MOF, so the model. As I said, the model is very simple, but now in this parametrization, we can see that we have the metric, and the metric changes with the position. So it's larger for some points, and it's smaller from other ones. So very specific points. And the Hamiltonian in this case, I said, is simple kinetic energy, and the total Hamiltonian is the sum of all these energies. And the nice thing is that the metric appears here. Where is here? Appears here explicitly. So to do this, we cannot do it analytically. So we did it numerically. So we used Forest root integrator to preserve this symplectic structure of the phase space. And because we have these collisions between the particles, and we have this curved space, we need to take into account that. So we use the parallel transport to transport effectively the velocities. So with all this, then, and it was nice because we have the physical velocity is constant. Well, under these assumptions, we have a very good energy conservation. So the mechanism is simple. So as I said, the physical velocity preserves. The energy is constant, the total energy is constant. But if we check the velocity is related with the angular velocity. So if the metric changes, the velocity changes, the angular velocity changes. And if the metric is larger in some points, the angular velocity has to be smaller. Then in those points where the metric is larger, we have that these particles start to go down slow. So here we can see that, for example, this is the angular velocity. This is how it behaves as a function of the angle. This is the time that they spend in these positions, and this is the density, and they are related with the geometry, with the metric. So here is how they behave. In the case of the circle, we don't have these clusters, it's homogeneous, but in the case of the ellipse, depending on the eccentricity, we can start to find some points where they have this clustering. And then, let me move a little bit more. If we check this density, the angular density, well, we can compare, we can see that this density is related, as I said, with the position, no? And let's say it's related with here is the curvature of the metric. No? So everything is nice, it's okay. And this is the density as a function of the eccentricity and the number of particles. But so far here, we saw that we thought that it was very close related to the curvature. So we went 3D just to check. And in fact, when we went to this 3D, The curvature and the metric was correlated because of this nice term, but the behavior of the particles are very close related to the metric. So we check that, and we find, well, we can see here really how the whole behavior, and we need more time, more particles, but it's a very nice simulation. Well, I think so. So the point is that in the angles where the metric is larger, we can see this cluster, and it doesn't depend. Well, it's not here. For example, we have the curve is more curved, but here, in these points, the metric is larger. And after some time, we started to see that they started to cluster here. Well, I don't know if I want to talk about this, but it's a little bit risk. But what we saw is that for eccentricity is larger than that 0.5, it doesn't. This cluster, the size of the cluster, the larger size of the cluster, it doesn't depend on the number of particles, and not even depends on the eccentricity. So all of this depends on the metric. So finally, something that, let me skip this, and let me check the phase space. So in the phase space, we can see here how they accumulate around these domains where the metric is larger. And finally, something that we see that is related is that, for example, in the case of MIPS, and in this work that we have this it's like analog of these MIPS, the factor that gives us this slowdown with the density is the geometry, the metric, and then well, that's all. And finally, I think it's okay. And finally, what we saw is that the intrinsic geometry, in this case, drives this spontaneous clustering, depending on the very important, depending on the parameterization. Our numerical method worked very well, and we have different domains depending on the eccentricity. There is not phase transition, but they are like two different phases living together. And this, well, temperature inversion. What I wanted to say is that in the case of the clusters, the energy inside of the clusters, because of the collisions, is, let's say, higher than the particles that are out of this cluster, and the particles that has less energy can escape from this cluster. And then that's all. Thank you.
Thank you. Questions?
So I'm puzzled. I mean, you're using the polar angle to characterize where your particles are, but if instead I used path length along the curve, would I not go back to standard hard sphere physics or hard particles physics?
Well, I had to do this intrinsically. These hard spheres are just pieces of the curve. So everything is like, let's say, from the point of view of these little particles. No? So in this case, they see a different. It's like when we are in the car, we see different things. No? I don't know if you understand your question. Maybe not.
Okay, just to rephrase the question, if I transformed from polar angle to path length along the ellipse, would your steady state not be a flat distribution?
No.
Okay, then I've not understood what physics you're putting in, but that's fine. I'll ask you later.
Thank you very much. Very interesting effects of geometry into the dynamics of the system. I was wondering if you managed to calculate stuff like if you could see anomalous diffusion, stuff like that, in terms of attack particle?
We didn't check. Well, there are a lot of things that they need to check, and that in particular, we didn't.
I have a question. Two simple questions, actually. First, in your point 2, you means the conservation energy, the energy conserves, and this is a numerical question. Is this what you mean, this ratio?
Yes, conservation of energy. In all the process, the energy conservation was in that order. Sorry.
You mean the energy conserves or not?
The energy conserves.
Okay.
Yeah.
Second question, sorry if it's too stupid, but you are dealing with a mechanical system. I didn't understand how the temperature enters, appears.
It's just the kinetic energy.
Okay. Okay. More questions? So let's thank him again.
Thank you.
So the next speaker is Yhony, Mamani. No. You are Antonio. Okay. Forgive me, please. Sorry. The next speaker is Antonio Ortiz. He will talking about artificial colloidal ice with anisotropic interactions.
Thank you very much. So I think the mic is working. All right, yeah. So I want to talk about this system, which is called artificial colloidal ice, which is something that we've been working on, or I've been working on for already quite some time. There was some anyway, so this system is a system that we use to explore frustration. So it's a model system for frustration. So just very briefly, because I don't think this audience needs a lot of introduction to frustration, but still, frustration is something that you get when you cannot satisfy simultaneously all the interactions in your system. And the most classical example of this is in the antiferromagnetic icing model. And the antiferromagnetic icing model is what, normally if you have two spins, you would want them to be antiferromagnetically aligned or antiparallel, and this would minimize the energy of the system. And the problem comes from having a third spin. No? If you put a third spin here, there's no good way to put it, so you will always have this bond here that it's frustrated. This button does not show the lighter. Yeah, I think. So what we did as a similar system to explore these types of interactions is to place a lot of colloidal particles. Sorry about that. A lot of colloidal particles in little double well traps. And originally we did this experimentally. I'll talk a little bit about the traps in a moment. And basically these particles are all, so in general you just need some way to trap your particles in some sort of B-stable potential, and you place your these B-stable potentials along a lattice, normally forming vertices, but that's something that we can play around with. And also you need some sort of interactions, and in our case we chose magnetic interactions because it's something that you can tune very easily from an external magnetic field. We did this experimentally originally, as I said, and this is the kind of videos that you get from it. And basically what we did was we covered a substrate with lithographically photoresist, and then you can etch the photoresist and you get these little holes. And if you do it correctly, you can sometimes get a hill in the center, which is not a very controlled hill, but you still get it, and you can measure it. And then, again, the particles are paramagnetic, so they repel. And they do these kind of behaviors. And in the end, you get something that usually looks like this. This is the kind of final states that you get in these systems. And these all you can classify through vertices, and these vertices are usually following something that we call the ice rule, which is that two particles are pointing in and two particles are pointing out. And this comes from, from ice structure where you have this ice rule for the oxygen atoms, hydrogen atoms, sorry. One thing that happens, because our system is flat instead of tetragonal, we lose the degeneracy that you get from ice, and instead we have something that looks like this. Normally, which is the whole system can be mapped by vertices, by these kind of vertices, which is vertices of type 3. And usually when we did this in simulations, which don't have this kind of quench disorder in the trap height from the experiments, you get something that is usually very well behaved. Here I didn't choose a very well behaved state, but in general, you get something, you start from a disorder, you make a quench, and eventually you get an ordered state, and if you wait long enough, these two lines will converge and form a whole state. Only this is a very long time, no? But not, thermodynamically long. So this is not usually the behavior that we expect. And one thing that we did was we tried to modify the magnetic field. Just basically, we were trying to recover the degeneracy, and it didn't quite work because we got distracted, which sometimes happens with the system. And what we get if you put the field in the in-plane direction along one of the directions of the lattice, you get a very different interaction, a much more complicated interactions, because your magnetic field, your magnetic interactions are no longer isotropic. Now you get this both this repulsive region. Sorry, this attractive region, the blue is attractive, and this repulsive red region. And you can see that if you put all your particles here, they all fall into the attractive region. So in general, you would expect, and I have a better slide for this, you would expect your system to fall into a state where all of the particles are concentrated in the vertex. So this is kind of like inversion of the normal colloidal ice that we were looking at. And we can calculate the kind of an effective energy that helps us build a mean field model. We just plug this into the Boltzmann distribution, and we see that this works usually very well for colloidal, regular colloidal ice. But when we do this change in the field, first of all we see that the energy corresponds, the lowest energy corresponds to a mixture of these type 1 and type 6. And the thing is that if we run Langevin dynamics or Brownian dynamics, which is what we usually do with this system, we don't see our model works terribly bad. No? So we always see this thing where we get a lot of vertices of type 3 and type 2, and type 5, no? Like couplings of these two pairs of vertices, which is what you can see here. And the typical video that you get from these quenches is something like this. So you start with a very disordered system, and eventually you get to this very disordered system, which is just slightly less disordered, or not necessarily, than the previous one, right? So if you look here at the time and the field, you see that we stop the field at some point, and then we continue running, and this is stable for about an hour. No? You get these kind of fluctuations, but they don't seem to be growing into anything. It's just like particles that are kind of undecided on where to go. If we go a lot slower, we get something that starts to form crystallites, but it doesn't really form crystallites. No, instead we have these. It forms crystallites. It doesn't really crystallizes. Again, as opposed to the normal isotropic interactions, now we get these kind of grain boundaries here. And the system, approaches a little bit the model, but still falls very, very far away. And basically what we're seeing is that the system becomes arrested in a metastable state, even when we don't have a quench disorder in the underlying lattice, which is something that, at least for me, was surprising. And the reason it happens, or at least the reason we found that it happens, maybe we could be wrong, but it's that to explain it, we went and looked at the potential around one of the traps, one of the vertical traps, and we see that as the field increases, the barrier that the particle needs to cross increases very, very quickly. And basically, it comes from the fact that this line falls inside the potential, the trajectory that the particle needs to jump, right? So this was kind of something that we found interesting, and yeah. So The next thing that we did was, this is a little bit different because here we changed the size of the particles, and especially we changed the effects of temperature. And so here temperature is much less important, right? So what we did is we start from an ordered configuration, and we're trying to figure out a way to change the field so we get to an ordered state. And this way that to get to an ordered state was not what we expected, because if we change the direction of the field, we measure, we take as the control parameter the velocity that with which we are changing the direction of the field, we find that for very fast processes, we get an ordered state, which is kind of the opposite from what we were looking at before, right? Of course, the system is quite different. And if we go at very low speeds, we get, so here where we're showing is the probability of the number of vertices that are in the ground state. So here we get something that is fully in the ground state, and all this region is things that are, in this kind of disordered states. If we look at well, so if you see the videos, we can see that for very fast quenches, we get to all particles have a very definite, a very definite trajectory that they need to follow. You just need to flip all the horizontal particles, right? And if you look at the trajectory along their line, all the horizontal particles for the very fast quenches, all the horizontal particles follow this trajectory that goes to the other side. And just vertical particles, start trying to jump, and then afterward, because this particle already jumped, they find, that their original position is better, so they go back. Whereas if you go very slow, sometimes it's like if particles got confused, no? So sometimes particles start jumping, even the vertical particle starts jumping before the horizontal one can find its way, and you get something that it's like, oh, sorry, this is the keys, no? You get something that ends up being disordered, no? So the system cannot find this very well-defined path. If you go very slowly, it's like it got confused. So this is kind of, puzzling for us. I don't have a much better explanation, but I do have a phase diagram, or something like that. All this, sorry, this is not the button. This region is not a very interesting region because it's just where we caught the system before it has a chance to relax. But all this, everything up from this line, this is where you get something that falls into an antiferromagnetic ordered state. Whereas this region here is where you get something that ends up being disordered. I think that's everything. Thank you very much. So basically, just as takeaways, anti-anisotropic interactions kind of induce this kind of freezing in colloidal ice, even if we don't have quench disorder in the underlying lattice. And the other thing is that if we start from an ordered state, faster rotations lead to more ordered final states than slower rotations. And with that, I just want to thank the people who have involved in the project, and especially Leo Alanis, who's the master student who did a lot of this work. And he's a very bright student, and is now in Singapore with Rani. So.
Thank you. Questions?
I have a question. These are very nice experiments and very nice experimental system. Do you expect your results also to be valid for some sort of material? Okay.
I don't know. Okay. If I did, maybe it would be nice to put it in the introduction, but I have no. I cannot think of anything right away, and I've been looking at stuff. But I'm not like an expert in material science, right? So. This is a material. Yeah, it's a
material.
It is a
synthetic material, right? Let's make the distinction.
Thank you. I was wondering about, did you try simulations with quench disorder in order to see what you're seeing experimentally?
No, but it's a good question. And we didn't because we kind of know what is going to happen. I mean, we are going to get disordered, probably more. But of course, yeah, maybe as a sanity check, it would be good to check if we have simulations. We have done simulations in the past where we put some, just like a distribution on the heights of the hill. but we didn't do it here. But thank you. Yeah.
Thank you. And if another question, if I may, the quenching protocols pretty much rotating the magnetic field, right? With a sinusoidal wave.
No. Which in the second case where we rotate? No. It's just so maybe maybe angular velocity is not the right way of putting it, but it's just we're moving the field from Z to X. It's just like a quarter rotation, and we're doing it at a fixed frequency.
How quickly it is. Okay, perfect. Thank you.
Let's think again. The next speaker is Yhony Mamani, and he will talking about active swimmers in SMATIC A, planar and focal conic configuration.
Okay, thank you. This work was developed during my master degree. And I am PhD student, and I am still working in this topic. So, and my advisor is Danilo Liarte. So, that is the organizer of this event. So, this is right. Okay, so let's start with the motivation and context. So, this work lies in the framework of the active matter, and that concern of the systems that operate intrinsically out of equilibrium, and we are interested in understanding how the self-propelled particle navigate when it's embedded in the complex fluids. So there are many examples of this. For example, this system, biological systems. So to modulate the component of this system is often used the active Brownian particle framework, and where the propulsion and the translational diffusion determine the dynamic of the particle. So in our case, we are this environment is the SMATIC A liquid crystal. And this SMATIC A liquid crystal possesses a layered structure. So, and the normal director is perpendicular to this layer, and the distance between this between the layers is constant. So, previous work showed this particle embedded in this SMATIC liquid, but in this case have some fluctuation, and this some results, for example, for this work is the mean square displacement have this anomalous behavior, and particularly for the perpendicular direction. So in our case, we have this static configurations. We don't have the fluctuations, and we are interested in these two kind of configuration of SMATIC, and also in 2 dimensions. So we can see this is a planar focal conic domains and a planar ground states. So, so to model the systems, the swimmer is modeled as a Brownian active Brownian particle, and with constant self-propulsion velocity, and the direction of the propulsion is coupled with the normal director, local normal director of the SMATIC, and the equation of the dynamics is given by these equations in our model. So the translational and the orientational equation, and the alignment energy given by this expression. So where the k is greater than 0, and also represents the alignment strength. So this energy is minimized when this propulsion direction of the self-propelled particle aligns or anti-aligns with the local SMATIC director, we can see, and that is which is consistent with the symmetry of the smectic A phase. So we restrict our model live in 2 dimensions. So in this case, we have the equation of motion for the x and y and angular directions. So, and also we define this relevant dimensionless parameters, that is a Peclet number, alignment term, and an isotropic ratio. So these parameters that control the dynamics of the system. So let's see some simulations for planar configurations. In this case, we have the normal directories pointing in this direction. So, for example, for alignment 3 and alignment 8, we can see the difference. So, for example, for alignment 3, we can see the particles is able to move significantly in the perpendicular directions and spread almost homogeneously. But in the case when the alignment is 8, the particle is restricted to move in a line. So it means the characteristic rotational times is greater than when alignment is 8 than when alignment is 3. So this is reflected in the mean square displacement. So we can see the ballistic behavior is here, and then we have the diffusion part, and the transition from a ballistic part and the diffusion part is shifted for different values of the alignment term. So we can see, and the same happened for the rotational mean square displacement. We can see a plateau. For example, for when the alignment is 10. This is a consequence because we are a strong coupling between the alignment term, and the direction propulsion, and the normal director of the smectic. So let's see. Now let's examine the effective diffusion. So for different values of the Peclet and alignments. So we can see the points represent the simulation data, and the lines is solid line is fitted. So we can see when alignment is 0, we recover the canonical active Brownian particle model. So and the coefficient that is expected, that is 1/2. But when this alignment increase to 4, for example, the blue line for 2 and for another values of the line, so this coefficient also increase. You can see, and to understand this, we take these values and define this we define this A function, and in this second plot we can see this A function. The dependence of this alignment term. The blue points are the simulated data, and the dashed line are the fit. So empirically, we can see this this A function is the dependence of this alignment term is by this function, hyperbolic cosine function. So this is, we are still working to understand how to get an analytical solution for this case. So some results from the analytical part. So for example, when alignment is 0, in this case we have the active Brownian particle. So for different values of Peclet, we can see the mean square displacement, and this is the simulated data, and this dashed line are the theory that predict. So the same happened for the effective diffusion. So, but if in this case we can see for different values of the alignment and a strong alignment, we get some analytical solutions for just for the ballistic part, but we are still working to get solution for the diffusion part. So Now, another configuration of this smectic liquid crystal is the focal conic domains. So this is the sum of these focal conic domains is the toroidal. So if I cut this in the middle, we can see this kind of arrangement. So we have the layers here, and the normal director is perpendicular to these layers. And as I interested in the 2 dimensions, we have this kind of configurations. So here we can see for different values of alignment, and that's fixed at fixed Peclet number. So for example, in here, the interesting thing about these systems is when we have the singularities. The singularities are in the middle of this cross section of the toroidal. So in this point, for example, the normal director is not defined. It's not defined, and also we have another singularity, this line. So the same here, but when the particle goes to the center of this toroidal, the particles is thrown to randomly in another directions. That is, obviously, this affect the dynamics. So in this case, we are still working in this part, and also we can see, for example, for this case, the pink color. So the particle, when goes to this singularity, it's moved like in following this normal director. So, so for some conclusions, geometry alone can regulate active transport. No layer fluctuation are required to produce non-trivial behavior. Smectic structure acts as anisotropic environment, and also analytical plus numerical agreement in planar smectic for a strong alignment. We are still working too far for diffusion part. So focal conic domains induce complex geometry dependence transport. So I would like to thank my advisor and collaborators, William Oropesa, André Vieira, and Harunari. Thank you.
Thank you. Questions?
I have a couple of questions. Any experimental evidence?
We don't have any experimental evidence, but no, actually no.
We can talk. Second question is, have you considered some feedback of the active particles on the nematic or the smectic structure in your case?
Sorry?
So in your case, you're showing that the smectic
is static.
Is static and aligns the direction of or rectificate the motion of the active particles, and you could expect a feedback in practice of the motion of the active particle on the orientation of the smectic. Is this something you've considered?
If I consider, I don't understand the feedback of the.
I can comment very quickly on that. In our model, we don't have feedback, so the smectics affect the active particle, but the active particle does not affect the smectics. If you think of the size of an active particle actually moving, there should be some anchoring around the active particle that would drive the smectic order somehow, and this is an interesting effect that so far we have not considered, but that's something that we can plan for the future, yeah.
Very quick question, please.
Okay, as far as I understood, there is translational and rotational noise.
Yes.
They are completely independent in the model?
Yes.
Okay,
yes.
Thank you.
It was okay. Let's think again. And
Better now? Okay. Yeah. Okay. This one goes here. This back over. Okay. So I would like to thank the organizers for the opportunity to present this. This is a work that I did with my undergrad student, Ryan, and we just sent this to archive last week. And this will be about opinion propagation in complex networks. And in order to understand why these opinion splits are interesting, I'm going to start with a kind of complicated question: why do we disagree with each other? If we consider society as a whole, we have what we call opinion diversity. No one agrees with each other. However, there's a lot of seminal experiments in psychology, like Ash's conformity experiment and Sherif's autokinetic experiment, that shows that if you have a small group of people, there's a high tendency for conformity on it. They will end up agreeing with each other. So if you try to model how people convince each other, you want to include this type of thing in your model to get something what we call a local conformity model. To give an example of what a local conformity model is, I'm going to talk about the Schneid model, which is what we used in our simulations. And the idea is to represent the network, the society by a network, where each side is a person, which we'll call an agent, each edge is a social relation like friends, family, and each agent has an opinion, which here has been represented by a color. Now, there are many flavors of the Schneid model, but they all boil down to picking two neighboring agents and checking if they agree. If they disagree, nothing happens. If they agree, then we try to find a neighbor of this pair, and the pair convinces this guy. Now, this is what we call local conformity. So we have a small group, and because the pair agreed, the whole group agrees now. The problem with this type of model is that if you keep doing this, no matter how large your network is, eventually everyone agrees, and this doesn't match what we see in reality. So there's something missing here. There's an extra ingredient that we need to add. Now, along the years, a lot of different ingredients were proposed to try to get back diversity. The most obvious one is trying to add some kind of thermal noise, so add the possibility of opinions to be changed at random. Something that it's very similar is the addition of contrarians, which are agents that don't follow the model, they do the opposite of what the model tells us. And these two modifications give us the type of transition of order-disorder that we're used to in statistical mechanics. Something that's very different is the idea of bounded confidence. So you have now opinions that only interact if they're similar enough, so you can have free states like left, center, right. Left and right don't talk to each other. So now you have the possibility of a frozen state, where everyone is either left or right. And finally, there's the idea of innovation, which that new opinions may appear in your network at random. Now, these modifications can create diversity, but they also bring new problems with them. In the case of noise and contrarians, the main problem is that the intensity of this interaction is kind of unrealistic. For example, for noise, you need to, at every 3 interactions you take, you completely change your opinion at random. So this is kind of weird if you think about the real world. In the case of bounded confidence, the main problem is that the final state needs to be frozen, and this makes the modification structurally unstable. If instead of left and right not talking to each other, there's now reduced probability of them interacting, this is sufficient to destroy diversity. You end up getting a consensus state in the end. And then there's a more subtle problem, which is what we analyze here, which is, in these models, if you start with M opinions, the diversity state you get has all of the M opinions equally represented. And this is also kind of instability, because if now we have the possibility of new opinions appearing, this means that the number of opinions will keep increasing until finite size effects kick in. So now you have the opposite problem. You don't have consensus, you have way too many opinions compared to what we see in the real world. And this leads us to the modification that we added in our model, which is opinion latency. This is a much less understood modification, which is the idea that once you change your opinion, there is a buffer time where you don't change your opinion again. And this is associated with opinions changes having a cost. You can think of this as like a social cost. For example, if I present as voting for some party, this might get me labeled some way. And this was something that was only studied for 2 opinions. So our main initial motivation was to see what happens if you add more opinions to this. Being a bit more precise, opinion latency is basically the idea you're adding an extra state to your agents. Now, they can be active or latent. If you try to convince a latent agent, nothing happens. The step fails. But trying to convince an active agent works as usual, but if you change the opinion, now you become latent, and after some time, latent agents can become active. We're doing this by adding a probability that a latent will become an active. Okay, so if we put this in a simulation, what the hell happens? Okay, these were simulations that we did in Barabashi-Albert networks with 10,000 sites and a minimum coordination of 3. And what we see is that if you start with a lot of opinions, the number of opinions decreases with time, but it doesn't go to 1 exactly. What we're seeing here is the average of the number of opinions in the network over 1,000 simulations. We have opinion batches starting with 3, 4, 5, 8, and 12 opinions. And we are ending up with an average with 1 or 2. And what we are getting here is that some of the simulations are ending in consensus, some are ending in a coexistence of 2 opinions. Something that's a bit counterintuitive is that if you start with more opinions, you end up with a smaller average. And this is because when you have more than 2 opinions, the asymmetry between the opinions increases until you get to 2, and then it might decrease. But if you start with a lot of opinions, this takes longer, the asymmetry becomes larger, so you might end up in consensus by the end of it. So this seems to suggest that if you have more than 2 opinions, you get some kind of unstable situation. We decided to check this with a bit more care. Now we look at time series of the number of opinions in the network. This is again 1,000 simulations, and we looked at this value of p, which is the one that gave us the longest lived states with 3 opinions, just to be absolute sure that this is what was happening. And we can say that we start with 3 opinions, and all the simulations end up with 2 opinions. So one thing that seems to be happening here is that situations with more than 2 opinions are unstable, but you can have coexistences between 2 opinions that are stable. Now, since we saw in the first graph that we can also get into consensus, this means that in some sense consensus and coexistence are stable at the same time, so they have competing basins of attraction. To probe this a little bit further, we focus now on the case with just 2 opinions. Here we have the parameter p, and this is how asymmetric my initial condition is, basically the proportion of the most common opinion minus the proportion of the least common opinion. So we consider we have a transition. If we increase p, which means that we are making latency shorter, we go back from coexistence to consensus, and if you increase the symmetry, the same thing happens. Now, to finish, we try to understand this in a bit more detail. We did mean field treatment. The idea is that you can think of this model in a complete network, go to the limit where the network is very large, and do one time step. And once we do this, you end up with a time evolution that is equivalent to integrating this in time. This is very similar to the talk that we saw before the coffee break, where you have the models in a space. Here we have an abstract space of social interactions, and here you have a kind of compartment model. And here eta sigma is the proportion of agents that are latent with opinion sigma. Nu sigma is the same thing for active agents. You can solve the fixed points of the model, do the linear stability analysis, all of that. You can do that all analytically. And this seems to be confirming the things that we are seeing in our simulations. All fixed points with more than 2 opinions are unstable. All consensus states are stable, and coexistences with two opinions are also stable, as long as you have a sufficiently high latency. You get the same competition between consensus and coexistence, so you also have basis of attraction. Just one small difference here is that in the case of the mean field, there's a difference if you start your initial condition with everyone active and with everyone inactive. The basins look to be a little bit different. In the simulations, we saw absolutely no difference. So in the simulations, we were starting always active. Okay, I think our time's getting to an end, so let's move on to the conclusions. Okay, so what I want you guys to take home from this is that even though opinion latency is also a modification that we can add to a model to move from consensus to diversity, at least in the case of the Schneider model, it seems to work in a fundamentally different way than the other modifications, because it doesn't have that instability of you being able to create an arbitrarily large number of opinions. However, the thing's not actually that simple. One thing that we did in the paper, and I didn't have time to talk about, is this. If you go to a different model, which is the Volter model, this instability appears there as well. So this is something that is still model dependent. So we don't really know what is happening to give us this cutoff in the case of the Schneider model. This is probably something that you need to look in very many different models to understand. Maybe there are models with higher cutoffs than 2 opinions. We don't know. Okay, just the archive for the paper, and
thank you very much for your talk. Questions?
Hands and
you said that you're working on the Barabasi-Albert network.
Yes.
Where you have, of course, hubs. And they are spreaders of opinion. So what is their role?
We didn't check how the network is, how the interplay between the network and the opinion propagation is happening. I am aware of a lot of papers, at least the very, very old ones by Stauffer, where he looked at style thing exactly in the Schneider model, but we didn't check this exactly. But I'm not so sure if this matters, because, for example, in the mean field, you're thinking about a complex, not a complex network, but a complete network, and the same thing happens. So maybe the hubs are not important in this case. Maybe they are, because you get qualitatively the same thing, but maybe it changes something quantitatively. I don't know.
Hello. I don't know, maybe you already mentioned it, but you were saying that opinion latency was really critical in the coexistence of coexistence and consensus. What if you have time-dependent opinion latency? Like, let's say you have different age, you're more susceptible to change your opinion. So if you have a time dependency in your opinion latency, what do you expect to see, maybe?
I have no idea what should happen. I mean, this is something that's very poorly understood, opinion latency. But I think that if the whole range is high enough, then we shouldn't see a lot of difference. But if there is a high range, for example, a lot of people with very low latency, a lot of people with very high latency, then I don't know, maybe there is some kind of competition here. Just to give a more concrete idea of the values that we had here. For example, this is something that we will consider low latency. This p equals 0.18 basically means that after like 6 interactions, you're open to change your opinion again. This would be a much higher latency. This would be like 33, 34 in average.
More questions? Let's think again, André. The lunch.